Look at the relations in the Xiphoin-Kempen theorem. And here's a simple picture to show why we need relations. Okay, let's take a cylinder and let's write it as a union of two sets. This guy is x1 from here to here, and x1, and maybe this chap is x2. Okay, so the region up to this is x1, the region up to this is x2. And of course each one has fundamental group Z because they are both deformation retractant to the circle. But on the other hand, the cylinder itself also has fundamental group Z, which is not the free product of Z and Z. The latter is the free group on two generators. And the reason is very simple. If we are looking at the intersection, and if I take a loop here, okay, perhaps I should draw it more accurately. We have a, maybe this was the base point which has to be in the intersection. The loop goes around here, comes around this way and comes back here. This is a loop in both x1 and y1. X1 and x2, and it's the same loop. So you can think of it in a fundamental group of x1 and then to x, and in the fundamental group of x2 and then to x, and you get the same result. So now the theorem, Xiphoin-Kempen theorem, tells you this is all. Okay, so let's look at the statement a little bit more precisely. The same thing about a loop here and there. So remember that we have now a collection. I'm going to again call it x alpha, alpha in A, because I and J are used for inclusions. So we'll live with the fact that alpha is also used for loops, but here it will be reserved for indices. So we have x alpha, alpha in A as spaces, subspaces of x, and they are open. Okay, and x0 belongs to intersection alpha in A of x alpha, and the union of all of these is x. So they cover everything. And now we have the hypothesis that for all alpha beta, x alpha intersection x beta is path connected. Okay, even before that we had the hypothesis that for all alpha, x alpha is path connected. And under this hypothesis we showed that we had a map phi which maps the free product alpha in A of pi 1 of x alpha with the base point x0 into pi 1 of x0 is on 2. Okay, and what does that relation correspond to? For that we want a little more notation. So let I hat alpha be the map which maps pi 1 of x alpha x0 into pi 1 into not the pi 1 into the free product of beta in A of pi 1 of x beta x0. So this is the algebraic map, which is an inclusion. Maybe I can put a star here because it's at group level, but this is not the map induced by inclusion into x. Instead it's the map which gives you the component in a free product. Okay, and that is the map that we are going to be. So what is the relation in terms of this map and another map? The other map is, let's say, j alpha beta. This is the map from x alpha intersection x beta into x alpha. This is an inclusion. And the above relation is, let's call this loop lambda. The above relation will tell you that if I look at I hat of alpha of j alpha beta of j alpha beta star of lambda, okay, and then let me put an inverse on the other guy. So this times, if now instead I go through beta, so which means I'm looking at I beta, okay, so I can put parenthesis here, I beta hat of j beta alpha star of lambda. Okay, so this is going to be so what we have done is we have taken the same loop lambda. Okay, so let me say for okay, so let's look at all this set here where all lambda belongs to the fundamental group of, indeed it's a loop, so let's be more precise and say the loop space of x alpha intersection x beta comma x0. Okay, let's just call this R, and alpha beta are indices. So for all indices, let's look at the image of the first one. I have to correct what I have written here. So I take an element lambda, so in a loop in the intersection, like the purple loop here. I can include it into alpha and then include it as a component in the free product, or I can include it into beta and include it in the free component, and these two should be the same. So if I take the inverse of the second guy, then R, any element in R is going to be trivial. So this is, of course, the whole thing is an element in the free product at alpha in A of pi 1 of x alpha x0. Okay, so both of these are elements in the free product, and the element in the free product has to be trivial. Okay, so that means we can say N is, it's often written like this, so the normal subgroup generated by R. Okay. So we have set up most of the statement. What we have said is that we have a loop, and if I take a loop, I can look at it as an element in x1 or an element in x2, and these will give you different elements in the free product, which is a purely algebraic construction, nothing to do with the space X. But when you view them in the space X, they are going to be the same. Okay, that's what we want to capture. So far we have not captured anything, we have defined these things, but we will capture in the form of a theorem. And the theorem is simply that kernel of this map phi which we defined earlier is N. That is, in terms of isomorphisms, phi induces explicitly pi 1, well, let's look at alpha in A, pi 1 of x alpha x0. Let's look at this free product and quotient it by N. This is mapped isomorphically onto pi 1 of x x0, but we need an additional condition. Okay, so provided for all alpha, beta, gamma indices, we need x alpha intersection x beta intersection x gamma is path connected. Okay, we need one dimension higher. I mean, we need one dimension in the sense of intersection higher, because we are going to be dealing with homotopies, which are going to be paths of paths. Okay, so our proof closely follows Hatcher, and let's just look at the first step here, which is some terminology, which is the factorization, as Hatcher calls it. So factorization, so any element in this product, in this free group, let's give it a name, capital F, blackboard bold F, because we're going to write it too many times. Okay, so elements in F, well, they are represented by factorizations. Okay. Namely, gamma 1 star, gamma 2 star. So let's say G is gamma 1 star gamma n. Okay, where there exists alpha 1 alpha n such that gamma I belongs to pi 1 of x alpha I and x0. So this is just like the word in the free group. We have not fixed the loops, but they're classes. So indeed it's a word in the free group. Okay, so on these we have an equivalence relation, and this is just the equivalence relation by which we explicitly constructed the free group, except we don't really need everything. So the equivalence relation says the following. Okay, and there is one more point, which is we have to take care of n. Okay, so the first point of the equivalence relation is that if we have alpha I equals alpha I plus 1, here the alpha is at the indices, okay, then gamma 1 star gamma 2 star gamma I plus 1, etc. star gamma n is equivalent, as you would expect, to gamma 1 star up to, and then this guy is written in this way, gamma I plus 1. Okay. Well, for a couple of reasons we didn't. So this is generated by the following. For a couple of reasons we don't need to delete E in the proof. Okay. But so it's clear that if two elements are equivalent this way, they give you the same element in the free group itself already. But the more significant thing is if gamma is in loop in x alpha intersection x beta and x0, okay, then not gamma but gamma I specifically, then regarding so let's say x alpha I intersection x beta, then regarding gamma I as a loop in pi 1 of x beta x0 gives an equivalent factorization. So this is not kind of clear what is going on here. Okay, so what is going on is the first relation is what we have in a free product. That is, we can combine two things if they came from the same guy. But if an individual comes from two different groups, this doesn't happen in the free product, but can happen in the spaces. Okay, then we will have we regard them as equivalent. Okay, so the easy proposition is the following. That is that if factorizations are equivalent, so if I have two factorizations of equivalent, so then they give, so any factorization gives you an element in the free group, but these give you the same element in free group quotiented out by n. Okay, and another fact which is easy is the following, namely that so also the proposition, we'll quickly look at the easy propositions and then turn to the work. The easy proposition also says that if I take an element in n, okay, then it goes to the trivial one. Okay, so that is to say kernel of phi contains n. Okay, so this is reduced enough to show kernel of phi contains R. Okay, so let's look at these one at a time. So let's look at the second one first. Well, we want to show kernel of phi is n. This is a theorem. The harder part will be the other way, that any element in the kernel is of this form. So this is saying that the relation, sort of obvious relations, are the only relations. That's the harder thing to show. The easy thing to show is that any of these obvious relations are relations. So kernel is a normal subgroup. So if it contains n, which is the normal subgroup, contains R, okay, then it is enough to show kernel of phi contains R. And let's remember R is generated by elements of this form, I alpha this times I beta this. Now any element of this form clearly goes to lambda lambda inverse. So if I took this element, okay, so this element here, this thing maps when I look at pi 1 of x0, this thing maps to lambda, the inclusion map, okay, times lambda bar, which is the identity. Okay, so that is the that's really by construction of this map, because inclusions don't change the loop, so it's the loop itself and the loop itself inverted, so that you will get identity element here. So since any such element which is in a defining element of R goes to the identity, so does all of R, so does the normal subgroup generated by R. So we see kernel of phi is n. So we want to show it the other way around. So what we have to show is that if we have if we have any two elements that go to the same guy, they are related by elements in n. Okay, and so that is, so this is F, of course. Here this is the group which we are calling F. Okay, so we want to have the map from F by n to pi 1 of x. And now if two factorizations are equivalent, okay, so elements in F are given by factorizations, represented by factorizations. Okay, so if you have two equivalent factorizations, we'll claim that they give the same element in the quotient. Okay. That is because if I took an factorization, gamma 1, gamma 2, gamma n, and two factorizations are related by the first move, they give you the same element in the free group already. So there is nothing, and hence of course in the quotient. On the other hand, if you have a gamma I which is being in the intersection, then the relation R corresponding to the loop gamma I, lambda is gamma I in that case, will tell you that the two words that you get, the diff are equivalent. Okay, so using the span of that relation, you will get that these two words are equivalent. So what remains to be shown? What remains to be shown is that if I have two elements in the left hand side given by factorizations and they go to the same guy on the right hand side, then they are equivalent words. Hence they will be equivalent in F over n, and hence the kernel is exactly n. Okay, so that is the main proof that we will turn to next.